detection of near-Earth asteroids has become increasingly important for scientific and planetary defense applications. Currently, there are more than 30,000 cataloged NEAs in the national database, representing an effort began in the late 1980s. However, thousands more have yet to be cataloged or tracked. This is a huge problem because some NEAs have very low albedo, which means they reflect very little sunlight. This makes them more difficult to detect with telescopes as they are not as bright as other objects in the sky. Currently, most NEA detection is conducted with ground-based telescopes because space-based telescopes are in extremely high demand, placing a premium on their time. Additionally, ground-based stations can be limiting due to atmospheric disturbances, light pollution, and increasing amounts of space debris in orbit. This is not an ideal solution because asteroids that can be difficult to detect in space become almost impossible to detect on the ground. To see clearly, we have to observe asteroids from space. For our senior project, we propose a solution to these challenges by developing an orbiting, deployable telescope for asteroid reconnaissance. This prototype telescope will revolutionize asteroid reconnaissance by allowing for dedicated low-cost, low-power imaging capabilities from orbit. The optical elements will be packaged into a CubeSat form factor for efficiency and low cost. The use case for this technology would be to fill a capability gap in detecting NEAs with very low albedo. The objective of this project is to demonstrate the capability to detect near-Earth asteroids approximately 0.3 astronomical units from Earth with albedos between 0.05 and 0.1 for scientific and planetary defense applications. This work also aims to demonstrate tensegrity-inspired mechanical deployment technologies in volume-constrained environments, maximizing both aperture and focal length.
Our initial goal for the optical system was to utilize a traditional Schmidt-Cassegrain telescope design and potentially manufacture our own primary and secondary mirror. However, we quickly learned the manufacturing of mirrors for telescopes is extremely difficult and expensive. We then decided to purchase a commercially available telescope and use the parts from the optical tube for our deployable structure. The next main challenge we faced was the placement of the camera within the volume of the CubeSat. In a traditional Schmidt-Cassegrain telescope design, the camera is placed a specific distance behind the primary mirror. For our project's purposes, this would drastically impact the amount of volume we have to store the telescope within the CubeSat. After speaking with the optical expert Scott Tucker at a local astronomy store, STARscope, he believed a product that they manufacture in-house would be a perfect solution for our problem. The Hyperstar, a multi-lens corrector, is a device that replaces the secondary mirror on a traditional Schmidt-Cassegrain telescope design to provide a method of securing a camera on the front end of the telescope. The Hyperstar transformed our optical system by making a wider field of view with extremely fast exposure times. This allowed us to be able to find asteroids in our images much easier than before. The first step in the testing process was to perform a first light test. Outside of the AME building on April 1st, we set up the optical system and were able to capture several images of the night sky. The test rendered beautiful images of the Moon, the Procyon star, and the M48 star cluster, despite there being lots of light pollution. The next test was to perform two separate objectives with the test in the desert. The two main objectives were to scan an area of the night sky for presence of a near-Earth asteroid, as well as take two images an hour apart in an attempt to track the movement of an asteroid. To attempt to perform both objectives simultaneously, we took a mosaic of each celestial body an hour apart with the hopes of finding an image with an asteroid that had moved within this hour-long window. Next, the team began the long, tedious process of data acquisition from over 200 images that were taken from this test. The online astrophotography tool, Astrometry, allows users to upload images and have them solved by identifying the main celestial bodies from the images. Additionally, the online tool provides the right ascension, declination, and field of view radius from the image. These values can be used in astronomy software such as Stellarium to replicate the image and allow us to find main stars, planets, or deep sky objects that are seen in the image. This process of identifying objects in images is continuing to this day, and we believe we will be able to identify near-Earth asteroids from the images we have taken. The goal of the structural design was to replicate a 6-inch Schmidt-Cassegrain telescope design, but have the optical tube itself be deployable to allow it to be stowed into a CubeSat. Early on in the design process, we decided to focus on a twisting method of deployment, which we believed would allow us to save the most amount of space for electronics and optical equipment within the specified volume of the CubeSat. Later on, during the development of the design, we decided to use an iteration process of several prototypes before manufacturing the structure to ensure the idea behind the deployment was feasible. The first model was a simple model built out of popsicle sticks and strings. This model brought what we theorized into our hands, but it was flimsy and difficult to work with. This made it difficult to determine if the issues from this model were due to construction method or oversights in the theoretical design. The next model was built out of laser-cut wood and 3D printed materials. The ball joints that we had originally planned on using were replaced by rotating hinges connected to rods. This model was an improvement from the first prototype, but had some of the same issues. Originally, it was theorized that by pulling on the strings from the bottom of the structure, it would be able to fully deploy. But with this model, it was seen that tension from the bottom was not fully enough to deploy the structure itself. The third model was constructed using the same materials as the second prototype, but with smaller tolerances, a different deployment method, and a second layer. To address some of the issues observed in the second prototype, this model was modified to enable tensioning of the strings both upward and downward, allowing for precise adjustments to control the movement of the model. The main issue with this model was the requirements of a long strut in each corner, which made us question the feasibility of the actuation. Our final iteration eliminated the use of cables to deploy the structure, and we instead decided to actuate directly at the hinges. This design choice eliminated a majority of the complexities of the design and multiple potential points of failure. This design slightly exceeds the size of our CubeSat, but with space-rated servo motors and a higher budget, this design could be modified to fit inside of a CubeSat. This design will also collimate the primary mirror with 3 stepper motors with a lead screw. This collimation process can also adjust and make up for potential heat warping and vibrational displacement of the structure during launch.
Setting out in our project, we wanted to design a collapsible, low-cost telescope that could detect near-Earth asteroids. Our project satisfies a niche in asteroid detection in its ability to find asteroids with low albedo and its competitive sizing and affordability. We're finally at the point where we're running tests to confirm our prototype functions properly, but the path to get here was not exactly obstacle-free. Throughout the process, there are a range of challenges, some anticipated and some not. An immediate and recurring problem we faced was a lack of experience regarding a major component of our project, optical systems. There was a lot to learn in a short amount of time, since everything had to be designed around the optics. Often the answer to a question was, "We don't know, but we'll find out." Another considerable difficulty was time. The fast-paced nature of the timeline we were on meant we had to set several in-group deadlines. We had to have a final time by this date so we could have our machine done by that date, so that testing and assembly could be completed by design day. And still, we find ourselves wishing for just a bit longer to work with. The deadlines helped us to get our project done, but it also meant if we thought of a better idea after the fact, we wouldn't be able to add it in. We're gratified by the prototype we put forward, but there are a number of changes we all wanted to make if neither time nor money were factors. We fit the vertical requirement of a CubeSat, but narrowly take up too much room horizontally. The main improvements we would have made center around size, weight, and precision in our servos, structural material, and additional equipment that would be used to verify configuration. These implements would have enabled us to fit properly in a CubeSat. However, the budget time constraint tandem made us get creative with solutions to our problems and pushed us. We all learned valuable lessons in this practical application of knowledge. Be flexible, be proactive, speak up if something isn't working right, or even if it is. We're proud of the product we created, and maybe one day a new asteroid will be detected using a design like ours.